So today, we're going to tackle one of the absolute biggest mysteries in the entire universe, the black hole information paradox. Think of it like a cosmic magic trick that seems to break the most fundamental rules of physics. And you know what? Solving it might just rewrite our whole understanding of reality itself.
Okay, let's just dive right in. Imagine two different situations. On one side, you've got a book, and it's on fire. It's turning to ash and smoke, and you'd think the information inside, all those words, is just gone, right? Now, on the other side, that same book falls into a black hole. Whoosh! It disappears behind the event horizon. To us, it kind of looks like both books were totally erased.
But, and this is a huge but, physics has this central commandment. You cannot destroy quantum information. It's a principle called unitarity. And it says that with our burning book, if you could track every single particle of ash, every wisp of smoke, you could, in theory, put the whole book back together. The information isn't lost, it's just really scrambled.
Black holes, though, they seem to be the one place in the entire universe that just flat out ignores this sacred rule. They're like a cosmic magician's hat. Things go in, and then, as we're about to see, the black hole itself eventually vanishes, and it looks like it takes all that information with it. And that, right there, is where our mystery really begins.
All right, so let's see how this whole thing snowballs into a full-blown paradox. And it's all thanks to a truly groundbreaking discovery by the late, great Stephen Hawking.
You see, Hawking figured out that black holes aren't these eternal prisons we thought they were. Because of some weird quantum stuff, pairs of particles are just constantly popping into existence all over space. But right at the edge of a black hole, sometimes one particle gets sucked in while its partner escapes. And as someone watching from far away, it looks like the black hole is giving off this faint glow, what we now call Hawking radiation, and is actually, very slowly, evaporating over trillions of years.
Okay, so here is the real kicker. Hawking's original math showed that this radiation is completely random. It's basically just thermal static. It has no structure, no pattern. It carries zero information about what actually fell into the black hole. It doesn't matter if it was a book, a starship, or your car keys.
So what you have here is this epic showdown between the two pillars of modern physics. On one side, you've got general relativity, which tells us how gravity works, and it says, yep, black holes evaporate. But on the other side, you've got quantum mechanics, with its absolute rule of unitarity, screaming, information can never, ever be lost. They just can't both be right. And that is the heart of the paradox.
So, to solve this cosmic case, physicists had to put on their detective hats and dig up some crucial clues from the incredibly bizarre world of quantum mechanics. The first clue is something called entanglement. You know that spooky action at a distance Einstein was always talking about? That's it. When two particles are entangled, their fates are linked no matter how far apart they are. What happens to one instantly tells you something about the other. It's like they're two halves of a treasure map. You need both to get the full picture.
And this is basically the smoking gun of the whole investigation. A physicist named Don Page figured out that if information is saved, then the amount of entanglement between the radiation and the black hole has to follow this exact curve. It's got to rise for a while, but then, and this is the critical part, it has to fall all the way back down to zero. So reproducing this Page curve became the ultimate test for any solution.
But of course, it's not that simple. There's this one really stubborn quantum law called the monogamy of entanglement. Basically, a particle can't be fully 100% entangled with two different things at the same time. And this seems to make a solution impossible, because a particle of Hawking radiation needs to be entangled with its partner inside the black hole, and it has to be entangled with all the radiation that came out before it if it's going to carry the information out. It can't do both.
Okay, we've got our clues. Now let's take a look at the lineup of suspects, all the different theories trying to solve this case of the missing information.
First up is an idea that is seriously gonna bend your brain, the holographic principle. It suggests that all the 3D information of everything that ever fell into a black hole isn't actually lost in its guts, but is perfectly stored on its 2D surface, the event horizon. Kind of like our entire universe might just be a giant hologram.
But here's the problem. If you try to save the information that way, you run into something terrifying. To obey that strict monogamy rule, the quantum links between particles would have to snap right at the event horizon, releasing an insane amount of energy. It would create a literal firewall, a wall of super hot energy that would just incinerate anything trying to fall in. And that totally violates Einstein's theory that crossing the horizon should be, well, no big deal.
So we were stuck, right? Break quantum mechanics or break general relativity. It seemed like a no-win situation. And then, in 2019, bam! A stunning breakthrough came out of nowhere that seemed to solve the whole puzzle, a concept called entanglement islands.
I mean, this was absolutely wild. This new calculation showed that to get the right answer for the radiation outside the black hole, you have to mathematically include a region inside it, an island that's deeply, quantumly connected to the outside. It's almost like the information found a secret quantum tunnel to escape. It doesn't break out, it just uses this new connection. And when you do the math with these islands, you perfectly get the page curve. Unitarity is saved, and you don't need a crazy, destructive firewall.
But, you know, like any good detective story, the case isn't completely slammed shut. The island idea was a huge leap for sure, but the debate among physicists is still raging.
See, the people who aren't totally sold on the island solution are pointing out that the math seems to require, well, tweaking Einstein's theory of gravity just a little bit. And at the same time, there's a competing theory that argues the information was never really missing at all. It was always available right at the edge of the universe. For them, there is no page curve. It's just a flat line.
And this is where it gets really interesting, because this whole debate isn't just about math and physics. It's also about, well, it's about people. The island idea, coming from some really big names and institutions, has gotten tons of attention and follow-up papers. Meanwhile, some of the critics and alternative ideas have had a harder time getting the same spotlight. It's a reminder that science is a human process, and sometimes the race to publish can get ahead of sorting out the really tough questions.
So where does that leave us? With a question that could change everything we think we know. Is it possible to our entire reality, space, and time itself isn't fundamental at all? Could it just be an emergent property, something that's built out of the connections and entanglements of quantum information? What started as a case of some missing information might just end up rewriting the rulebook for the entire universe.